Hello and welcome to the final part of Lesson 3. In the previous parts of this lesson, we've examined how to set up Cauchy's momentum equation along with its boundary conditions so we can model various flow situations. So far, we've mostly dealt with problems simple enough to have analytical solutions. Well, that is until we saw the problem for the radial flow of a power law fluid in cylindrical coordinates. A problem that was relatively straightforward to solve for the Newtonian case required numerical solution for the power law case, as the differential equations became rather nonlinear. In this part of Lesson 3, we're going to examine how to set up and solve numerically a slightly simpler problem, but one that has great relevance when dealing with flows of non-Newtonian fluids. We're going to examine the flow of a Carreau Yasuda fluid in a pipe. To start with, we'll once again set up Cauchy's equation for the flow scenario, but we've done this already for pipe flow for a number of times now, but let's just remind ourselves what we did and how we did it. So, on the whiteboard there, once again, first thing, I've got my diagram of the flow. It's pipe flow, we've seen this before. We've got a pipe of radius R1, of length L, and across that length L, our pressure varies from P1 to P0. We're dealing, of course, with a pipe, so it's cylindrically symmetric, so I've got my axes there, centred on the symmetry line of the flow. The next step we did was to make a whole host of assumptions. These assumptions are identically the same assumptions that we've made for pipe flow before, namely that the flow is steady, that there's no spatial acceleration and no temporal acceleration. We're neglecting gravity because our pipe's horizontal. We're assuming that we've just got velocity in the z direction. There's no radial velocity, there's no tangential velocity. And that axial velocity, that z-direction velocity, just changes with radius. Thinking of pressure, it changes along the course of the flow in the z-direction. Okay, then what we did, if you recall, was we sketched a little fluid element and looked at the forces, pressures and stresses acting on it. And so our little fluid element has a pressure differential P1 minus P0, which has to be countered by the stresses on the radial face in the z direction, tau rz. So we've got a cylindrical geometry, centre line symmetry, axes on the symmetry line. In terms of boundary conditions, we've got a velocity maximum on that centre line, so that's where we have zero stress, and we've got no slip on the stationary walls, so Vz equals 0 and R equals R. So if you're coming at this afresh and any of this is unfamiliar, please go back to a previous part of this lesson where these steps have been explained in a lot more depth. So once we'd got our assumptions set out, we went to Cauchy's momentum equation. There we have rho dv by dt is going to be our body forces, gravity, plus stresses due to surface forces, pressure and deformation. And because we've got no temporal acceleration, no spatial acceleration, the total derivative d by dt of v is equal to 0. We're neglecting gravity, so all we have is the interplay of stress due to deformation and the pressure field. Grad p is equal to the divergence of the stress tensor. And exactly as before, we've simplified this down for our flow geometry. We've just got flow in a pipe, and that pipe just involves tau rz in terms of stresses and pressure varying with axial location. And so the differential equation that we arrive at is exactly the same as it was for the last time we looked at pipe flow. Tau rz is partial dp by partially z r upon 2, which we then link to the rheology of the fluid, which is going to be a measure of viscosity, eta, multiplied by the magnitude of the strain rate tensor. Okay, nothing new here whatsoever. Now, this is where we start to put the difference in. What we're going to say now is, of course, we've written eta there, not mu, and so eta, therefore, is a variable viscosity as described by the Carreau Yasuda constitutive law, which I've put there on the whiteboard for you. So it changes with strain rate magnitude, and there are a number of parameters that describe, for example, the location of the low shear rate Newtonian plateau, eta 0, the high shear rate Newtonian plateau, eta infinity, the characteristic time scale, lambda, and then something about the shear thinning in terms of A and M. So let's think boundary conditions. Well, our boundary condition is that our velocity is 0 when r equals r. Fine, okay. we've just got a first order differential equation. We only need one boundary condition for that. And we have a nonlinear first order differential equation. If we look at the form of eta, how it involves the magnitude of the strain rate tensor, and how tau rz also involves the product of eta and the magnitude of the strain rate tensor. So we need a numerical solution. Now, we're going to use Mathematica to find a numerical solution. So let's talk a little bit about Mathematica and why I've chosen it. Firstly, Mathematica is a long-established and very powerful piece of mathematical software from Wolfram, and it allows the numerical solutions of ordinary differential equations and partial differential equations to be found without having to know a great deal about numerical methods. And that's the crux of why I've chosen it for this particular course. It's because I haven't got time to teach you numerical analysis as well. I'd be quite happy to do that, and I have done in the past, but we haven't got the time to do that. So, Mathematica is also rather useful for a whole lot of ancillary things like solving equations analytically, if you want to check your mathematics. So that's kind of useful. Okay, so Mathematica is useful, but it's commercial software, so where can you get it from? University of Wisconsin members can download this and install this from the University of Wisconsin software repository free of charge. There is a site license for it, for the latest version, and you're at liberty to install that on your own personal device. However, the Raspberry Pi Foundation has got an agreement with Wolfram Research that Mathematica is on every single Raspberry Pi mini computer. So if you've got a single board computer, the Raspberry Pi, it will have Mathematica as part of its software suite, which is brilliant because it opens up access to anybody who can get hold of a Raspberry Pi. Okay, so we're going to establish a workflow as to how to solve this problem. We're firstly going to set up the equations and their constants within the Mathematica script. We're going to solve them numerically and look at the answer. And then we're going to be very, very careful how we check that answer, just to make sure that we can actually believe it. So let's start with step one. Let's set the problem up. We've already set up the mathematics. We've looked at Cauchy's momentum equation. We've set up the equations for pipe flow. We've included the Carreau Yasuda rheology. Let's code it. So the first thing we're going to do is just simply set some parameters. I want to define where my low shear rate Newtonian plateau viscosity lies in terms of its viscosity value, where the high shear rate Newtonian plateau viscosity lies. Also, I want to define the characteristic timescale and the other parameters that are associated with the Carreau Yasuda model. And the statement in Mathematica to do that is really quite simple. The curly brackets there basically mean you're defining multiple parameters at once, with a comma separating each one, and I've just given them arbitrary names that broadly describe what they are, and I can relate back to the equation that they come from. Okay, next step. Let's set the constitutive law. Now, the constitutive law of the Carreau Yasuda model involves my two plateau viscosities, my characteristic timescale, and my other two power law type parameters. And so there on the board in a big blue box is the Mathematica script for that. And if you compare that to the statement of the Carreau Yasuda equation, hopefully the two correspond pretty closely. So I've got my parameter eta inf, which is eta infinity, my high shear rate Newtonian plateau viscosity, eta 0, my low shear rate Newtonian plateau viscosity, and then I've got lambda, which is the same as lambda, A and M, which are the same as A and M. Now, the shear rate here is simply dVz by dr. We've established that before by looking at the strain rate tensor and by examining the components that aren't zero. And so dVz by dr in Mathematica is evaluated by just saying, well, I've got my velocity v, its derivative is v dashed, the parameter with which I'm taking the derivative against is then in square brackets. So v dashed of r is dv by dr. Okay. So the next thing I want to do is to set some parameters for the geometry and for the flow. And this is where we need to think a little bit differently, because I'm not going to get an expression that says, for a certain fixed volumetric flow rate, I have this pressure drop. It's the other way around, because volumetric flow rate doesn't feature in the equations of motion that we've derived. But pressure drop does. And so I'm going to set the pressure drop and then find out what velocity field results from it. If we wanted to, we could then iterate to find out a given pressure drop for a specified volumetric flow rate. but I'll just take that first step to start with. So I'm going to assume a pressure drop, let's say 10 to the 6 pascals per metre, and let's see what flow results from that. So second step, solve the problem, look at the answer. The Mathematica for script for that I just put in this big blue box, and let's take this section by section. And I've colour coded each of the sections so we can see which bit that I'm talking about. So ND solve, that is Mathematica's inbuilt numerical differential equation solver. So that is effectively a command, and that is the command that we're going to issue to solve our differential equation. It returns an answer which is going to be parked into the parameter solution, because we've written solution equals ND solve. And solution is just an arbitrary name. I could have called that anything. ND solve, however, needs to be spelt exactly as put on the screen, since it is actually a command. So the first thing that appears within ND solve is a statement of the equations that we're solving. And there in red is delta p times r divided by 2 times L times e to c minus v dashed of r double equals, assignment, 0. And that's just the statement of the equation of motion that we've derived from Cauchy that I've put there on the board in algebraic form for you. The next thing that appears is the boundary condition. We've only got one boundary condition, remember, because we've got a first order differential equation that we're solving. And that boundary condition is effectively a statement of no slip. Okay, the next thing that appears in ND solve is the parameter that we're solving for, v, which is shorthand for vz in this particular instance. Then we have the range of radii for which we're calculating vz. So from the centre line of the tube, 0, to my internal radius of 0.005 metres. Okay, so the text in green there are just some specifications to the numerical solver, which allows the solution to be obtained with stability and with speed. Okay, so if you issue that command, the differential equation will be solved very, very quickly. And we've already defined e to c previously, and for each iteration it'll just update what that viscosity actually is according to the Carreau Yasuda model. Okay, the next thing we need to do is to just plot out an answer and then scrutinize it rather carefully. So the plot command will do that. We need to extract the velocity field from the solution, and the syntax of the plot command I've put there on the board will extract those data for you and plot them over the range of r that's then specified in curly brackets. And I've chosen that range of r to be the same as the range of r that we've solved the original set of equations for. Right, okay, so let's plot some things out and see what it looks like. There is a plot of velocity as a function of radial distance from the centre line. For the parameters e to infinity is 1 pascal second, e to 0 is 100 pascal second, and for the various values of other constant parameters I've put there. So it looks all right. I mean, it's plausible, isn't it? I mean, it goes through a turning point at r equals 0, and it goes to 0 when r equals big R, or 0.005. It doesn't crash. Okay. There's an answer. Do we believe it? The default position any numericals work I would recommend is that you do not trust the answer until you've proved that you can. So what we're going to do now is to validate this and make sure that we can believe it. And we're going to validate this as follows. We need to think of a way in which we can manipulate the Carreau Yasuda equation to give us an answer that we know. Ideally, an answer we've got an analytical solution for. So, first off, why don't we adjust the Carreau Yasuda parameters to give us a Newtonian result, and then compare the numerical solution that we get to the analytical solution for Newtonian fluid in a pipe. Okay. Then we might want to test it a little bit more stringently. And we might say, well, why don't we shift the Carreau Yasuda parameters to one or other of the Newtonian plateau viscosities and test it that way? You might at this point ask, well, what's the difference between the two? Let me show you. So, our Carreau Yasuda constitutive equation is as follows. We've got our variable viscosity e to c being a function of e to infinity plus the difference of the plateau viscosities times a bunch of terms that then involve the shear rate. The simplest check we can do is knock out all the parts that have a power law variation and a dependence on gamma dot. So if we set eta 0 equals eta infinity, the second part of that equation on the right-hand side is equal to 0. And we just revert back to eta c equals eta infinity. Now, the reason why that's the first thing to check is because it'll check whether or not we've written the code correctly, whether we're solving the equation correctly, and whether we're extracting the solution and plotting it out correctly. All the nonlinearities in the problem are going to be avoided, so if there's any numerical problems, we isolate them to the second stage of testing. What we're testing to start with is whether we've just got the correct structure of the problem. So let's do that to start with. So that graph there is a function of velocity as a function of radius. The dotted red line is the numerical solution we've achieved from Mathematica, solving the differential equations that I've discussed how. The yellow line is the analytical solution for a Newtonian fluid flow in a pipe, and they correspond. That's great. Okay, good. So our first step of testing is quite promising. We've turned off the nonlinear component of the differential equation. We've run the solution. We've got an answer, and it corresponds identically to the Newtonian answer that we're expecting. Good. Now, let's redo this and include the nonlinearity and see whether anything falls over. So, the way we're going to include that nonlinearity and still give ourselves something to check is by manipulating lambda such that over the range of shear rates that we expect for the velocity in the pipe, we're kind of in the plateau region in terms of either low shear rate Newtonian plateau or high shear rate Newtonian plateau. And I can get a feel for the range of variation of shear rate simply by looking at the previous answer for the Newtonian case of, well, that's my Newtonian velocity profile. That gives me a feel for the shear rates involved, somewhere between 10 and a few hundred reciprocal seconds. All right, okay, for 100 Pascal second viscosity. If I drop the viscosity a bit, then my shear rates go up a bit. And so I can estimate broadly whether I'm comfortably in the low shear rate Newtonian plateau or comfortably in the high shear rate Newtonian plateau. We don't have to know exactly where we are there, we just have to be somewhere there. So let's start with the first case. Let's put ourselves in the low shear rate Newtonian plateau and let's see how the numerical solution and the analytical solution for a Newtonian fluid of that plateau viscosity correspond with each other. So here we are. The first thing you'll note is that the flow velocities are a lot lower. Well, that's expected because for the given pressure driving force, for a fluid of greater viscosity, we would expect the flow field to be smaller in magnitude. Again, the dashed red line is the Carreau Yasuda numerical solution with the parameters I've put there on the whiteboard, and the yellow line is the Newtonian solution. And if we look at it glancingly, we see, oh yeah, they match. Good. If we look at it carefully, we'll see that at 0 radius there's a slight divergence between that yellow line and that red dotted line. And we need to think about that. Why? Well, that is where we're really dropping our shear rate to 0, isn't it? So, are we still in the region that we think we're in? But the correspondence is excellent. Let's do one final test and put ourselves in the high shear rate Newtonian plateau region. And again, we're manipulating lambda to achieve this. And again, there's really good correspondence. And if we look at the velocity magnitude, we're 100 times higher than we were before, which is in line with expectation, possibly. And we can see that not only does the numerical solution contain all the features that we expect from the boundary conditions, no slip and no shear stress on the centre line, we've also got excellent correspondence again with that Newtonian solution. So we have now gained trust in our numerical solution. So we can now use our numerical solution for a flow that spans that shear thinning region or spans a shear thinning region plus a plateau viscosity, because we can trust the results, because we've proved to ourselves we can trust the results. Okay, let's summarise with a few key points. We've solved Cauchy's momentum equation again, but this time for the flow of a fluid with Carreau Yasuda rheology in a pipe, something that you cannot get an analytical solution for. We've followed the same workflow that we've used a number of times now. We've looked at the geometry of the problem, we've made a load of assumptions, We've simplified Cauchy's momentum equation down to the bare bones of what we need to solve, and we've extracted from that the specific differential equation we're solving along with its parameters. This time, that yielded a differential equation that was nonlinear that required numerical solution, which we obtained using Mathematica. Very quickly and very straightforwardly. We only had to issue about 6 or 7 commands. We didn't have to write any code, and we didn't have to understand any numerical analysis. What we spent most of our time doing was validating. And if there's one key point I want to really get across in this final part of Lesson 3, is the importance of validation when it comes to numerics. It is a crucial exercise. You cannot believe a numerical model without validation. So it's the first thing you do. You must always gain trust in your answer rather than assume it's correct at the outset.